The compute bottleneck holding back humanoid robotics was just shattered, and legacy AI chipmakers are running out of answers. Internal silicon testing data leaked out of Tesla's Giga Texas AI lab reveals the custom AI5 chip taped out with an incredible 8x compute leap over AI4. While Silicon Valley competitors were fighting over GPU supply chains, Tesla quietly built an in-house inference board engineered strictly for physical embodiment. Featuring local Grok-level neural processing and direct VLA model execution on-device, this hardware leap allows 1 billion Optimus bots to perceive, plan, and reason in real time with zero cloud latency. We aren't just looking at another routine hardware iteration, we are witnessing the birth of the largest decentralized physical AI network in human history. For years, the robotics industry hid a massive, embarrassing secret behind flashy promotional videos: physical robots were digitally blind and critically slow. When a humanoid robot attempts to navigate a dynamic factory or a cluttered home, it isn't just taking photos. It must continuously process high-resolution video streams from multiple camera angles, run complex spatial occupancy networks, predict human movements, and execute precise joint adjustments every single millisecond. Traditional robotics startups relied on third-party data center GPUs or cloud computing to offload this immense computational burden. But cloud processing introduces high latency. A 200 millisecond delay caused by a spotty Wi-Fi signal is the difference between a robot smoothly catching a falling glass and smashing it onto the floor. To bypass this lag, legacy developers tried cramming generic graphics cards directly inside the robot chassis. But server-grade chips were never built for physical embodiment. They are massive power hogs that generate blinding thermal heat, draining the robot's battery in under 30 minutes while requiring heavy, noisy cooling fans. Legacy chipmakers assumed that building an ultra-compact, high-bandwidth inference computer capable of running massive multimodal AI models on less than 300 watts was physically impossible until the 2030s. They believed that compute constraints would keep humanoid robots tethered to rigid industrial tracks or dependent on cloud servers for years to come. But while legacy semiconductor firms focused on selling general-purpose hardware, Tesla was quietly designing custom silicon built specifically for embodied spatial intelligence. And the leaked benchmarks from Giga Texas reveal that the traditional AI hardware hierarchy hasn't just been challenged, it has been completely overthrown. To understand why traditional chipmakers like NVIDIA and Qualcomm are scrambling, you have to look directly at the physical silicon powering AI5. While traditional semiconductor giants build generalized chips littered with legacy display drivers and server bloat, Tesla stripped away every unnecessary transistor. The new AI5 system-on-chip is engineered strictly for embodied spatial intelligence, delivering an astounding 2,500 TOPS of localized compute power, an 8-fold jump over AI4 with a staggering 40-fold efficiency leap in specific neural network tasks. Tesla solved the critical memory bottleneck by integrating 192 GB of unified LPDDR5X memory directly around the compute die. This massive pipeline provides up to 1.5 terabytes per second of memory bandwidth. Instead of waiting for off-site data centers to send back motion coordinates, Optimus Gen 3 executes vision language action models natively on the robot's onboard system. By consuming under 300 watts of power, this dense silicon board gives the robot continuous, high-speed spatial reasoning without draining its torso battery or requiring bulky cooling systems. And then there is the software integration. AI5 doesn't process camera data frame by frame like a standard computer vision setup. Using an integrated neural processing unit, it ingests multi-camera video feeds as a unified 3D vector space, calculating spatial depth and object velocities instantly. When an Optimus bot encounters an unfamiliar object in a dynamic environment, local Grok-level reasoning allows it to evaluate physical properties, predict potential hazards, and adjust its biomimetic fingers on the fly, all without a single byte of data leaving its chassis. When industry analysts calculated the infrastructure required to run 1 billion autonomous humanoids, they predicted a massive cloud compute crash that would bankrupt any company attempting it. But the real-world metrics coming out of Tesla's Giga Texas testing completely invalidate those traditional assumptions. Instead of burning through millions of dollars in cloud server fees to process basic spatial tasks, each Optimus Gen 3 bot operates as a completely self-contained AI node. Onboard local inference slashes external bandwidth requirements to absolute zero during active operation. Running at a mere 250 to 300 watts of power draw, the AI5 chip processes full vision language action models locally while preserving battery life for up to 8 continuous hours of physical work. When you scale this architecture across millions of units, the macro picture shifts dramatically. A fleet of 1 million Optimus humanoids equipped with AI5 silicon collectively generates 2.5 exaflops of local, mobile compute power. That is more raw processing capacity than the world's top 10 supercomputers combined, operating continuously in homes, factories, and supply chains across the globe. Every single robot acts as a mobile data gathering sensor. When an individual bot encounters an unfamiliar situation, such as handling a novel tool or navigating an unusual environment, the edge case visual telemetry is compressed and sent back to Tesla's central dojo superclusters. The central network updates the core neural parameters, and a refined intelligence model is pushed back out to the entire global fleet through over-the-air updates. By eliminating dependence on third-party hardware suppliers like NVIDIA, Tesla isn't just cutting build costs by an order of magnitude. They are building a self-reinforcing hardware-software flywheel that compounds its intelligence advantage with every single unit deployed. The ultimate existential threat to legacy semiconductor firms isn't just that Tesla built a faster chip, it's that they are building an industrial factory engine designed to mass-produce it at an unprecedented scale. While competing tech companies line up with open checkbooks waiting for third-party chip foundries to allocate limited manufacturing supply, Tesla has fully integrated the AI5 supply chain directly into its vehicle and humanoid production architecture. By designing custom silicon, board packaging, and cooling assemblies entirely in-house, Tesla drives the physical build cost of the AI5 computer down to a tiny fraction of what legacy hardware suppliers charge for off-the-shelf server boards. The target manufacturing output for these dedicated humanoid chips is designed to scale directly alongside Optimus production lines in Texas and California, ramping toward millions of boards every single year. At a retail price target of sub-$20,000 for the complete Optimus Gen 3 unit, the onboard AI5 computer represents one of the most cost-dense computing platforms ever put into mass production. To put this disruption into perspective, a legacy industrial robot equipped with a basic vision system and proprietary external compute modules can easily cost over $100,000, while remaining restricted to rigid, pre-programmed tasks. Tesla's AI5-powered Optimus delivers fully autonomous spatial reasoning, multimodal voice processing, and real-time physical adaptivity for less than 20% of that cost. Tesla isn't just selling a piece of custom hardware. They are weaponizing vertical integration to flood the global market with cheap, scalable physical intelligence that legacy competitors simply cannot match. The scaling of the AI5 silicon ecosystem doesn't just revolutionize individual humanoid robotics, it completely upends the geopolitical balance of computing power. Historically, global artificial intelligence was heavily centralized inside vast, power-hungry data centers owned by a handful of tech conglomerates. These facilities required gigawatts of dedicated grid capacity, millions of gallons of water cooling, and billions of dollars in infrastructure just to process remote queries. By deploying custom AI5 inference chips straight into millions of mobile Optimus units, Tesla is creating a decentralized compute architecture that operates outside the limits of traditional server farms. When millions of Optimus bots sit idle or recharge on home docks overnight, their AI5 boards don't go dark. Using local grid connections, these distributed nodes form a global, high-density edge network capable of running background inference tasks, fleet simulation learning, and complex spatial modeling. Instead of relying on central data centers, physical intelligence is distributed across the entire planet, running locally at maximum efficiency per watt. Traditional semiconductor firms and cloud infrastructure providers find themselves trapped in an unwinnable race. While legacy tech firms spend hundreds of billions buying external compute chips to rent out cloud bandwidth, Tesla is placing superior custom silicon directly into revenue-generating physical hardware that pays for itself. When every factory floor, warehouse, and private residence hosts an autonomous humanoid equipped with 2,500 TOPS of localized AI processing power, the world reaches an inflection point. The compute bottleneck is permanently gone, the reliance on third-party silicon suppliers has vanished, and the era of distributed, infinite AI compute has officially arrived. When localized AI silicon turns every humanoid robot into an independent supercomputing node, the line between hardware manufacturing and AI dominance completely disappears. The chip design is locked, tape-out is complete, and the AI5 production lines are scaling up for mass deployment. Will Tesla's custom AI5 silicon allow Optimus to completely run away from the robotics competition, or can legacy chipmakers find a way to break Tesla's hardware monopoly? Drop your thoughts in the comments below.